Welcome to the course module of speech signal processing. And in this video, we are going to discuss about the minimization of mean square prediction error to calculate the values of alpha case that we have already discussed in my previous lecture. So in my previous lecture, I had already explained you about about the general concept of linear prediction. And we had already seen that this prediction error will be given by this particular equation. En equals to Sn minus sum over k equals to 1 to p alpha k s into n minus k. Okay, S n minus k, right? So here we have to evaluate these values of prediction coefficient or predictor coefficient alpha k. And to get these values of alpha k, we have to actually go for the minimization of mean square prediction error. So in this lecture, we are going to see how this minimization will be done, how to calculate this mean square prediction error, okay, that we have to see in this lecture. So let's begin this discussion. So first of all, we have already seen this is the prediction error equation. En equals to Sn minus S cap n, where this Sn was the actual sample and this was the predicted sample, right? So basically here we have to do a little bit modification into this particular equation. So this equation will be get modified by considering a certain properties of the space signal. So first of all, you have to understand that the space signal is a random signal, right? So it is a random signal, and why it is random? Because the vocal tract shape of human is not constant over the time. So not only the vocal tract shape, but the excitation that we are using, for example, for the voiced speech, we are using the periodic impulse train, and for the unvoiced speech, we are using the noise. We are using the white noise. Okay. So in such cases, because these excitation and both vocal tract shapes are not constant, and therefore the signal or the speech sequences generated by this its equivalent model is not going to be constant. Okay, it is a time varying function. So not only a time varying function, but it will be a random signal, right? So normally, when we consider a speech of, let us suppose if it is of a 9-second duration or 10-second duration or more than that, okay, normally it will be consist of huge number of samples. So we cannot find out these values of alpha k for the entire duration of your speech sequence. But normally what we do is first we have to split this entire speech sequence into a smaller segments, right? So here in this speech signal processing, it is normally considered that this speech signal is actually being considered as a stationary signal for the smaller time duration, such as 10 milliseconds to 30 milliseconds durations. So normally in such durations, what we consider is the vocal tract shape or excitation of the speech signal is not changing, and therefore this signal can be considered as to be stationary signal, right? So normally what we do is first, whenever we are recording the speech signal, we have to go for the sampling. So let us suppose if we are sampling any speech signal, okay, and the sampling frequency is to be 8 kilohertz, then normally if we choose a 20 millisecond frame, in that case, this 20 millisecond frame is corresponds to 160 samples. So normally what we consider is we will be taking the 160 samples as one frame, okay, and the next 160 samples will be considered as the second frame, and so on, right? So what we have to do is we have to split this entire speech sequence into a smaller frames, and the frame size is going to be 160 samples, right? In this case, because I have just considered the sampling frequency equals to 8 kilohertz, and the frame duration is of 20 millisecond, right? So within this duration, we have to evaluate these values of alpha case, right? Which is our predictor coefficient, right? So normally this equation, whatever I have shown here, okay, will be a little bit mathematically modified, okay? Just to emphasize which particular portion we are considering for the evaluation purpose, right? Because we are not going to consider the entire speech sequences. So normally you will find that what we have to do is this Sn will be replaced by this Snm. Okay. So here this Snm definition is nothing but it is equals to Sm plus n, which is multiplied with a particular window Wm. Okay. Similarly, this En will be denoted by now Enm, okay, and which is equals to En plus m. So normally what we have to do is, suppose if we want to just consider this first segment, okay, right from 0 to this particular up to this sample, if we want to consider, what we have to do is we have to multiply a appropriate window up to this sequence, okay. So rest of the samples will become 0 and this particular segment will be multiplied with a particular window, and then only this many sequence SSP samples will be considered for the evaluation. Similarly, if you want to just consider this frame, okay, if you consider only this segment of this page, in that case the window is going to be multiplied at this particular section, and then only this many of samples will be considered for evaluation of your alpha case, right? So this way actually we have to first windowed the speech sequences by multiplying it with the proper window, okay, of proper length, and then we have to consider only those many samples of the speech signal for the evaluation of your alpha case. So let's try to understand what we mean to write this particular equation, how we have arrived to this particular equation, okay. So let's try to understand by having this particular equation, okay. So SNM is equals to Sm plus n into Wm. So here you try to understand this Wn is going to be a window. This could be a rectangular window, Hamming window, Hanning window, or any other window, okay. So here this Wm is 0 outside the interval 0 to n minus 1, right? So it will be just defined within this particular range, and after this range, and this window is going to be 0. So here I have just plotted a rectangular window for the simplicity, and here you can see it is only defined in between m equals to 0 to m equals to n minus 1. So now you consider this is our speech sequence, okay, as m plus n. So here what I am doing is I am just taking this m as the to denoting you the sample index. Actually, it is denoting you the sample index Sm, okay. M will be denoting you the sample index. So here I am just considering the first case when n equals to 0. In that case, this will be our Sm, okay. So this is the same as your Sm. So here you can see this is the speech sequence that we have, okay. And here we have the different number of samples marked here, okay. And it is going up to a certain values of m, okay. If it is considered, let us say if it is having 40,000 samples or 60,000 samples, based on the duration of your speech signal, this value of m will go up to that particular sample index, right? So now if you multiply this two signal together, you will find that only samples from m equals to 0 to m equals to n minus 1 will be getting the emphasis, right? Because outside this, this window is going to be 0, and therefore all the samples outside this range, when it is multiplied with the window, will become 0. And therefore only these many of samples is going to be considered for the analysis. For example, if we assume this n equals to 160, we consider the window size is equals to 160 samples. In that case, this index of m will vary from 0 to 159, okay, because we are considering the 0th sample here. So from 0 to 159, it will be giving you 160 samples. So this way only first frame will be considered, and we perform our analysis. Now suppose if we want to consider the next frame, okay. So obviously this next frame will start from m equals to 160, okay, and it will be moved from 160 to next frame will go up to because you have to add 160 there. So you just try to add that value. It will be, I think, 320 or 300, 119. Okay, so that will be the next value. Okay, that will be the range of your next frame. Okay, so it will be coming at 160, m equals to 162, 319. So that will be giving you total 160 samples in the second frame. So here you can see, if you wish to consider the second frame, in that case, this n value will be equals to 160, okay, because we have to start the frame at sample number 160. So if you do that, then obviously this particular signal Sm will be left shifted, okay. So once it will be left shifted, then this 160th number of sample will be shifted to m equals to 0. So here I have just marked that one, okay. So this all samples has been shifted by 160 and therefore this second frame will be shifted left hand side, and now it will be come in the range of this particular window. So now if you multiply this window, then again this second frame will be considered, and the rest of the samples will become 0 after multiplication with the Wm. So either you can shift the window or you can also shift the signal. Okay, the point is that we have to only consider that particular frame in which we are going to perform our evaluation, okay, to get the values of alpha k. So either you can shift this signal or you can shift the window. So here in this case, while defining SNM equals to Sm plus n into Wm, we are actually shifting this speech sequence, okay. So now you must be clear that this SNM means we are actually emphasizing a certain segment of the speech sequence, okay, such that the particular frame will be considered, okay, and this evaluation will be performed to get the values of your alpha case. So here what we have to do is this prediction error that we had already defined by this equation En equals to Sn minus k equal to 1 to p alpha k Sn minus k. Now here this Sn will be replaced by Snm and this En will be replaced by Enm, okay. So here now we have to define this mean square prediction error. So mean square prediction error will be calculated by having this definition of this particular mean square prediction error, okay. So En will be equals to sum over m En square m, okay. So we have to square this error, okay. We have to square this particular error, okay. And obviously because we are talking about the mean, okay. So first we are calculating the square of our prediction error, okay. We are calculating the square of the prediction error, and obviously we have to perform this square for this range of m, okay. So here I have not explicitly defined this value of m, but it will be definitely depending on the window length, okay. So if it is window is varying from 0 to n minus 1, this summation range will also vary from m equals to 0 to n minus 1. So here I am not defining at present, because in the case of autocorrelation method that we are going to discuss in my next video, so there this range I will be defining properly, okay. So what should be the range? So here you try to understand for a certain range of m, we have to square this particular prediction error En, okay. And then because we are talking about the mean square, this value should be divided by the total number of samples. But just for the simplification, what we did is we have just omitted that the total number of samples. We are not dividing it because it is not affecting the calculation of alpha case. So that particular division by the total number of samples can be omitted for simplification, right? So here we are considering this En equals to this particular summation, which is known as the mean square prediction error. So now you can substitute for this equation of En, okay. So this En will be equals to this Sn minus sum over k equals to 1 to p alpha k Sn minus k. The only thing is that this will be replaced by Snm, and this will be replaced by again Sn m minus k, right? So now this summation will be run over m, okay. And now we have to minimize this equation, because we are I have already said that to get the values of alpha k, first we have to reduce this error, okay. We have to reduce this error. So normally we are not directly reducing the error, but what we do is we actually calculating the mean square prediction error, and then this mean square prediction error will be minimized, right? So we have to minimize this particular equation En. So to do that, what we have to do is we have to go for the differentiation of this mean square prediction error with respect to alpha case, okay. And then we have to put that particular differentiation value equals to 0. So what we do is we perform this particular differentiation, dou en upon dou alpha k equals to 0, and this will be done for k equals to 1 comma p comma 2 up to p. So these are the values of different predictor coefficients, because we have considered the pth order predictor, and therefore there will be total p different predictor coefficients, right? So that corresponds to k equals to 1 to p, right? So now if you perform this differentiation of this equation, you please see this equation. If you perform this differentiation of this equation, okay, so if you differentiate it, we will be getting, after differentiating this particular equation, we will be getting this factor 2 outside. The summation will be over m. And then this first factor we will be getting as Snm minus sum over k equals to p alpha k Sm minus k. Okay. So again, we have to differentiate this particular factor. So you try to understand, because this alpha k is present in this particular summation, you can consider this to be like 1 minus x. Okay. So it is in the form of 1 minus x square, whole square, right? So because when this differentiation is with respect to x d upon dx, in that case, if we are having any function 1 minus x whole square, then this differentiation will be something like 2 1 minus x, then again d upon dx, and the differentiation of 1 minus x. So it is something in that form only, right? So if we perform the differentiation of the second function, dou upon dou alpha k, this value will be a minus sum over k equals to 1 to p alpha k as n minus k. So now we have to actually evaluate this particular differentiation. What will be the result of this particular differentiation, we have to see. So to consider that, what we will be doing is, because this k value is varying from 1 to p, okay, so we have to consider a particular value of k, which will be having the range from 1 to p. So let us suppose we want to get the ith linear predictor coefficient. Okay, ith linear predictor coefficient. Obviously, this ith predictor coefficient means its value will be in between 1 to p, right? So let us say we are interested in alpha I. Okay, so just make this correction. It is alpha I. So alpha I, then this k will be equals to I. So what we have to perform is we have to differentiate this dou upon dou alpha k, where this value of k is going to be I. So I'm just substituting here, it is I. Okay, and if you expand this summation, right, from k equals to 1 to p, we can write this equation as here it will be alpha 1. Okay, this is alpha 1. Just make this correction, alpha 1 Sn m minus 1, then minus dou upon dou alpha I alpha 2 Sn m minus 2. Then again we are having this alpha I Sn m minus I, then this summation will go up to alpha p Sn m minus p, right? So now you can see that because here we are differentiating the equation with respect to alpha I, and here this value is alpha 1, so this entire term will become the constant, and therefore this differentiation will vanish. Similarly, this differentiation will also vanish because we are differentiating with respect to alpha I, and here we have this coefficient as equals to alpha 2. Similarly, here again, all these values of differentiation is going to be vanished, but the only differentiation which is going to survive is this. Okay, so it is with respect to k equals to I. So because here this coefficient value is alpha I, so here we can perform the differentiation, and this differentiation will give you this result, because alpha I, if you perform this differentiation will be equals to 1. So here this will be becoming constant. So this result of this particular differentiation is nothing but is equals to minus minus Sn m minus I. So for all these values of I, right, from 1 to p, this particular differentiation will be replaced by this particular equation minus Sn m minus I. Okay, so now what we can do is we can substitute this differentiation equation, okay, this result, okay, of this differentiation into this equation number 3, right? So if you do that, this equation number 3 can be rewritten as dou en upon dou alpha I equals to minus 2 sum over m s nm minus sum over k equals to 1 to p alpha k s m minus k, and here we are substituting this Sn m minus I. That negative sign I have used here. This is the negative sign, okay? And here this value of I will be ranging from 1 to p. So now what we can do, we can expand this particular summation. Okay, so what we can do, we can just multiply the summation inside this particular bracket. So if you do that, you'll be getting this equation as minus 2 sum over m Sn m multiplied with Sn m minus I plus 2. Then this is summation over m, and the summation over k equals to 1 to p alpha k Sn m minus k into Sn m minus I. So now what we have to do to get the values of alpha k, normally what we do is after differentiation, we have to go for the calculation of the minima, right? So this differentiation value should be equals to 0, right? Because we have to minimize this differentiation, right? So this particular this differentiation value is going to be 0. So if you substitute that, then if you substitute 0 and then if you rewrite this equation, then this equation will become a sum over Sn m into Sn minus m equals to sum over m k equals to 1 to p and alpha k Sn m minus k Sn m minus n. And here this values of I, obviously it will be ranging from 1 to p. Now again, if you see this equation, we can just modifying it a little bit. So here this m minus I am writing first, and then this SNM term, and then k equals to p. I'm just interchanging this summation order. Okay, so we can first write this k equals to 1 to p, and then summation over m, and then alpha k as n minus I and Sn m minus k. So here we can also see that because yeah, this alpha k we can write outside this summation, right? So we can rewrite this equation in this form also. So it will be Sn m minus I into Sn m, and this right hand side can be written as k equals to 1 to alpha k sum over m Sn m minus I into Sn m minus k. So now this particular summation, okay, this particular summation is actually the definition of the covariance, right? So what we can do is we can define this equation as the covariance, which is known as the short time covariance of a signal SNM. Okay, so normally this equation is defined as the covariance. So the definition of the covariance is phi n I comma k, which is equals to sum over m Sn m minus I into Sn m minus k. So after having this equation, if we can rewrite the equation number 5, okay, so here you can see this equation number 5 that we have written here. So it is Sn m minus I into Sn m. So what we can do is we can just write this equation Sn m minus I, and here we can write Sn m minus 0, okay, which is equals to k equals to 1 to p alpha k, and this is sum over m Sn m minus I into Sn m minus k. So now here you can see this left hand side, this particular summation, and here in the right hand side, this particular equations, this particular summations are equivalently as this definition of your short term covariance. Okay, phi n k, phi n I comma k. So now by using this definition of short-term covariance, we can rewrite this equation by this particular summation. So here you can see this particular equation. Okay, first of all, what I am doing is I am writing this right hand side here in the left hand side. Okay, in this particular equation. So if you see this, this summation is ranging from k equals to, this summation is going from k equals to 1 to p alpha k, and then here this summation will be replaced by the definition of short-term covariance. So it will be phi n I comma k, and here in this right hand side this equation is same as the covariance, but the k value is equals to 0, right? And therefore this equation can be written as phi n I comma 0. And here you can see this particular equation. For this particular equation, here we have the range of I is actually having from 1 to p, right? So now obviously you can see this particular equation reflects you the p number of linear equations. Okay, there is a p sets of different linear equations. So here you can see if you expand this k, this particular summation over k, then obviously this term will become here you please make this correction, this is not ak, it is alpha k. So here you can see this value will be alpha 1, phi n 1 comma 1. First of all, we have to choose a particular value of I. So let us suppose if we expand this particular summation for I equals to 1. So in that case, this equation will become like alpha 1, phi n. Here I value is 1 and k value is 1. Then again I value is 1, then k value is 2. Similarly, this alpha k value will become alpha 2. And this this summation will go up to alpha p phi n 1 comma p, right? Because the last value of k equals to p. And this equation is corresponds to I equals to 1. So whenever you write this p sets of linear equations, okay, obviously you will be able to write this equation, right? So this is the first equation corresponds to I equals to 1. Similarly, this equation you will get corresponds to I equals to 2. Okay, similarly, you can write more equations, and the final equation corresponds to I equals to P will be this equation. Okay, so it will be alpha 1 phi n P comma 1 plus alpha 2 phi n P comma 2, and this will be alpha P phi n P comma P. And here in the right hand side, you will be getting this phi n P comma 0. So now here you can see what we can do is you can represent this p sets of linear equation in the form of matrices. Okay, so these matrix coefficients are you can see here are the matrix coefficients phi n 1 comma 1. Then again the next coefficient will be phi n 1 comma 2. Then this matrix will the last term of the first row will be phi n 1 comma p. Similarly, here you can write all the other rows, okay, based on this particular equations. And here we are going to get this column vector of all the our predictor coefficients alpha 1, alpha 2 up to alpha p. Okay, and here again we are having this values of covariance phi n. Okay, 1 comma 0, 2 comma 0 up to p comma 0. So now you can see this equation by having this particular matrix, okay, we can get the values of all this predictor coefficient right from alpha 1 to alpha p. And these all alpha values are actually calculated in the form of covariance, okay, this particular covariance. And you see this all covariance actually depending on only speech sequences, right? So, just by having this speech sequence, you try to understand this fact because initially when we started this discussion, I already told you that this alpha values we have to evaluate just by using these speech sequences, right? So here we can see this all short-term covariances, whatever we have defined here in this matrix, will be actually calculated by having this particular covariance equation, which is actually depending on only onto the speech samples, right? So now from this matrix, we can use any matrix solving algorithms, or by having the some programming in the computer, you can easily calculate all these values of alpha k. So here we can calculate all the alpha k's by using this particular equation, right? So now once we have done with this, and once we have calculated these values of predictor coefficient, what we can do is we can calculate what will be the minimum mean square prediction error, right? So you remember this equation of your minimum mean square prediction error. Okay, so this was the prediction error, mean square prediction error equation. So if you substitute the values of alphas, okay, whatever we had calculated by using this particular matrix, okay, whatever we calculate, okay, so whatever be the results of this alpha, if you substitute these values of alpha, then the obviously we are going to get the minimum mean square prediction error. Okay, so here you can just expand this equation again. Okay, and if we do this expansion, Sn m minus sum over k equals to 1 to p alpha k s n minus k. Okay, if you do this expansion of this expression, obviously just you consider as a minus b a whole square, and then if you apply this formula, you will be able to show that this equation will be sum over m Sn square m minus 2 Snm multiplied with this summation runs from k equals to 1 to p alpha k Sn m minus k plus You remember here, we are going to get the square of this particular summation, right? So instead of writing the square of this summation, okay, what we can do is we can write just two summations, okay? Multiplication of the two summations. And what we did is, you can see here, I have just chosen this particular summation index, which is varying from k equals to 1 to p, alpha k Sn m minus k. And again, I'm just choosing another sample index, L equals to 1 to p, okay? Alpha L Sn, summation index is L, okay? Sn m minus L. So there is no change, there is nothing harm in just choosing the different summation index, okay, because it is reflecting the same summation, you remember, okay. So this way we can write this this particular product term, okay, of this particular expansion of this particular equation. So here you see, if you see this term, okay, either this term or that term, okay. So what I'm doing here is that if you see this L equals to 1 to P alpha L S and M minus L, this equation is nothing but it will be the predicted value of your signal SNM, okay. So it is going to be the predicted value of your SNM, right? So whatever be the space sequence, that particular space sample, actually this particular equation will give you the predicted sample of that particular actual speech, okay. So here this equation is nothing but the estimation, or you can say the prediction of your actual speech sample. So because the values of alpha L, whatever we are substituting here, is corresponds to that values of alpha L, which is minimizing the error. So in that case, what we can consider is that this predicted value of SNM will be almost equals to SNM. So why it is almost equals to SNM, that you please try to understand, because here we have already minimized the equation of En. Okay, we have already minimized here, right? And after minimization technique, we have calculated the values of alpha case, right? So once we have calculated the values of alpha case, and if we substitute these values of alpha case into this estimation equation, this prediction equation, in that case, this prediction will be much equal to the actual value of your sample. And therefore, this predicted value can be written as approximately equals to the actual sample SNM, right? So now, just by having this fact, what we can do is, again, we can rewrite this particular equation, okay? A little bit modification I did is, here you just see this equation, I have just multiplied the summation inside this parenthesis, okay? So this summation will go over m, so it is SNM, Sn square m minus 2 SNM. So this summation will go inside, okay? So after multiplication, this summation I have written over here, it is SNM. Then this summation is running over this particular term I have written here, k equals to 1 to p alpha k Sn m minus k. Then this again, this summation will be multiplied here, right? And now I have just replaced this entire sum is equals to SNM, right? So after writing this here again, what we can do is we can do a little bit modification into this equation. So this equation can be further rewritten as this term I have written as it is, okay? And here I have just made one changes, that what I did is I have just changed the order of this summation, right? So here we can write k equals to p to 1 to p, and this alpha k term I have written outside, and then again this summation m, summation over m, then this is the our term SNM multiplied with Sn m minus k, right? So here you can see this value is this particular summation. Again, what we did is, again, we have done the same thing. We have just interchanged the order of summation, k equals to 1 to p alpha k, sum over m, then SNM Sn m minus k. So here you can note down one thing, that here this term and this, both the terms are same, okay? Both these terms are same, right? So here this factor is minus 2, and here this factor is plus 1. So if you subtract this, you are going to get this term as sum over SNM square minus this term, right? So because if you are subtracting, we are just getting this term with negative sign, right? So now just what we can do is I have already written this term here after subtracting. So here you can see this sum over m, and what I did is this Sn square m can also be written as Sn m minus 0, Sn m minus 0. Okay, so here you can see, because we are defining the covariance. Okay, so we have already defined this short term covariance as phi and I comma k. So in that equation, this I and k both will become 0, right? So this can be written as phi n 0 comma 0. Okay, and now here you can see this particular equation. This will be this is m minus I. So here I value is equals to 0. So what we can do is we can write this as again in the form of covariance. So that equation will become phi n 0 comma k, and here is our this predictor coefficient alpha k. So by just having this particular equation, okay, En equals to phi n 0 comma 0 minus sum over k equals to 1 to p, and we have to substitute the values of alpha k that we had calculated previously, right? So this is the corresponds to the values in which we have minimized the mean square prediction error. So after minimizing, we have got the values of alpha k. If you substitute it, you will be able to get the value of minimum mean square prediction error. So now I will stop here in this lecture. Okay. So we will be seeing another means method of finding this value of En, and obviously the finding the values of alpha k. So here you see this alpha k's are actually calculated in terms of the covariance, right? So I will show you that instead of just having this covariance, what we can do is we can also have the this matrix elements can also be replaced by the corresponding autocorrelation function. So that I'm going to discuss in my next lecture. So I will stop here in this lecture. If you having any doubt, let me know with your comments. So thank you for watching this video.